Now there's another piece of information that's very important here. For example, let's say we have a wagon. We're pulling a couple kids in the wagon. So we're pulling on the handle with some force F. Is that whole force responsible for making the wagon accelerate and move? No. That force can be broken into components. It has a component that's parallel to the ground. It has a component that's perpendicular to the ground. Only one of them makes the wagon actually speed up and move along the ground. Which one? The X-way. That means only the X component does any work. The perpendicular component does not do work because the wagon doesn't move perpendicular to the ground. When we talk about work here, the force and the distance have to be parallel. Have to be parallel to each other. If they're not parallel to each other, you need to find the component of the force that is parallel to the displacement. And there you go. You will have your work. Okay? So for example, let's say the total mass of the kids and the wagon is 70 kilograms. Let's say we're pulling with a force of 200 newtons. Let's say there's a coefficient of rolling friction. It's going to be awfully small, 0.02. Let's find the work done by this force. Let's find the work done by friction. There's also, of course, a normal force and gravity. But the normal force and gravity in this situation are not doing any work because they're perpendicular to the direction the wagon's moving. The wagon's moving along the ground. I'm assuming you're not lifting the wagon and dumping the kids out of the wagon, so you're not lifting it off the ground. Okay? Sorry, what?
Don't you need the normal force and the force gravity to calculate the coefficient of friction?
We will need the values, yes. Sorry, that's not a normal force too. Sorry, that's G. We'll need the values, because yes, the magnitude of the force of friction depends upon how big the normal force is. That's true. But the normal force in and of itself is not doing work. Okay? So the work done by our 200 Newton force, work done by our force F. Well, it's only this component. Oh, sorry, I guess I didn't give you an angle. It's only the X component that's actually doing the work. That's the component parallel to the direction the wagon is moving. So we need our 200 newtons times the cosine of 40 degrees. That's our X component of the force, the component of the force parallel to the direction the object's moving. And then we need to multiply it by the distance the wagon moves. So different amounts of work are going to be done depending upon how far we've moved the wagon. So we just need to decide how far we want to have moved the wagon. Let's say we've moved it 2 meters. In the process of moving the wagon 2 meters, we will have done 306 Newton times a meter is a joule when we're talking about energy. So that force does 306 joules of work. That means 306 joules of energy are put into the wagon. That's why the wagon moves. It puts energy in and giving it kinetic energy. Okay? Positive work means you've put energy into your object. Thus, you've sped the object up. or you've raised it up off the ground, that sort of thing. The work done by the force of friction. Well, the force of friction is parallel to the ground already, but it's backwards. It's opposite the direction of motion. So it's going to be negative mu times the normal force, and then our distance. So we need to figure out our normal force first. Is it going to equal mg? Have you really forgotten all of your forces? Come on. Absolutely not. How could it possibly equal mg? If the normal force equals mg, what is going to happen to this wagon? It's going to accelerate upwards. If this equals this, then it has a net upward force acting on it. And it would accelerate upwards, and they would go airborne, which might be fun for them. But it doesn't happen. The normal force cannot equal mg. Sum up the forces in the y direction. You have the normal force upwards. You also have this component upwards, so 200 newtons sine of 40. You have mg downwards, so minus mg. Because our wagon is not accelerating perpendicularly to the ground, that all has to equal 0. So our normal force is equal to mg minus the 200 newtons sine of 40. So we said the mass is 70 kilograms total. G we know is 9.8. So our normal force will be 557 newtons. It's less than mg, and that's because of the component of the wagon handle. So our work done by friction, negative, mu is 0.02. Our normal force magnitude is 557 newtons. The distance our wagon has traveled is 2 meters. So we're going to get negative 22. Awfully small compared to the work done by that other force. This one was positive. This one's negative. Work is a scalar, meaning it's just a number. Positive and negative don't mean to the right or to the left. I could certainly have drawn my picture so that we were pulling the wagon to the left, and we would still get a positive for the force F and negative for friction. So what do the positive and negative signs actually mean? It has to do with energy transfer. What does it mean to have positive work? You're putting energy into the system. Exactly right. Putting energy into the system. You're giving it potential and kinetic energy. Negative work means you're taking energy out of the system. You're taking away some of its potential and or kinetic energy. What the system does overall, with that equation over there, depends upon the net work done. This equation, work here, is the net or total work done by those external forces.
Just to clarify, the only reason that the force normal didn't equal the mass times gravity is because of the y component of the handle.
Correct.
Correct?
Yes. Normal force, only time the normal force equals the force of gravity is if there's no other y components of forces. Exactly. So our network, let's see, is 284 joules. So that means on a whole, we're putting energy into this system. The wagon and kids, we're putting energy into the system. Thus, we're either going to give it kinetic or potential energy. In this particular case, let's go ahead and put that in. 284 joules is our net work. That has to equal the change in potential energy plus the change in kinetic energy. How much is the system, our wagon and kids, how much is their potential energy changing? It's not. Their height hasn't changed. There's no spring connected to them. So there is no change in potential energy. That means all of this work done went into changing the kinetic energy. Remember, change of anything is final minus initial. So this will be the 1/2 mv final squared minus 1/2 mv initial squared. If we assume it started at rest, V initial would be 0. So all of that work, the 284 joules, gives the wagon kinetic energy. The kinetic energy is 1/2 the mass times however fast the wagon is going, squared. So V final will be the square root of 2 times 284 divided by the 70. .8 meters per second. Okay. Now, we certainly could use the net forces, find the acceleration. In this particular case, as long as we maintained that 200 Newton force, the acceleration would be constant, and we could use kinematic equations. So we're basically looking at another way to solve something we've solved before.